BR, major product is tertiary.
Yes. So in the last class we have started discussing about preparation of haloalkanes, right? So and we finished till free radical substitution reaction mechanism, that is halogenation of alkanes, right? So in the last first we have started discussing about classification, basic classification and their IUPAC name. First IUPAC name and the next classification, the next preparation methods. These are some preparation methods I have given right now. Detailed discussion is also done for this. So what is the use of Lucas test? We can distinguish primary, secondary, tertiary alcohols. Okay. Now what is a Lucas reagent here? Anhydrous ZnCl2 and concentrated HCl. That's it. Okay. And now I also told you there is some mechanism like SN1 and SN2. We will discuss about that. Okay. So now tell me what are the type of mechanism followed by these reactions when it is PX3, like when the reagent is PX3 or PX5. This in two cases you will be getting SN2 type of product. Okay, what is the type of product formed? Inversion product, that is SN2. When we are discussing about SOCl2 and like SOBr2, here we have SOCl2 is preferably used here. Thionyl chloride, this is the best method for preparation of alkyl chloride I discussed right now. So now here the configuration, it means if reactant is having R configuration, product is also have R, that is what retention product you should say, retention product here, retention. Okay, that is for SN1. Okay, I will explain that. Okay, and whenever we have thionyl chloride along with the pyridine, so here inversion of configuration takes place. What happens here? Inversion. Okay, you need to remember this when it is inversion, when it is retention, inversion. Okay, so when if the starting material, if the substrate is chiral carbon having chiral center or the chiral carbon OH group is reacting, then inversion of configuration takes place when it is reacting with PCl3, PCl5 type of things. Okay, then that is what we are saying, inversion of configuration. If it is SOCl2, it is a retention. Okay, SOCl2 along with the pyridine, inversion again. Okay, that's it. These are the discussions we completed in the last class. The next Lucas reagent and its applications also we discussed, right? Okay, next.
Yes, mechanisms.
This from hydrocarbons, like by free radical substitution we discussed. Like what is the reactivity order I told you? Fluorination, next chlorination, bromination, iodination. Whereas fluorination cannot be handled, it's very violent, whereas iodination is very slow. It can be possible in presence of some oxidizing agents like HiO3. Okay, so it means this method is not preferable for fluorination and iodination. It can be useful in case of chlorination and bromination. Now I told you chlorination is more reactive and then bromination. A more reactive substance have less selectivity. So chlorination is more reactive and less selective we discussed, and then proper exact calculation of amount of product also we did based on the experimental observation. Okay, then next, what about alkyl groups reaction? See, rate of reaction of alkanes. If there is a tertiary carbon hydrogen bond, so that will be more reactive when you compare with the secondary. Least is primary, that's it. Okay, now tell me what will be your answer. How many monochlorinated products are formed by butane upon chlorination? Tell me. So how do you answer this? How many monochloro products are formed by N-butane? See, it's very easy. N-butane means it is like this. Okay, so first of all identify type of hydrogen. See, these two hydrogens are of same secondary carbon containing hydrogen. So this is like A type I am saying. Now what about these methyl groups?
B type.
This is B type.
So 2 types.
Okay, now do chlorination at this terminal side once. Like this it is first. Here chlorine. Okay, next here also you can do chlorine. Okay, now what about the product formed here? See, this is at this. So terminal, is this a chiral center? No, product is not a chiral product. So only one product. Okay, what about this one? 2 chloro means yes, here you have a chiral center. See, chlorine is one group, this is ethyl, this is methyl, one hydrogen. So I can arrange chlorine above the set, below the set. So we will get one chiral center here. So one chiral centers, number of 2 power n, that is 2 power 1. So it means two products, one is R, another one is S. Okay, you got R and S. So whenever we have R and S, now tell me how many isomers are possible here, monochlorinated products are how many? So 3 are possible here. Okay, so you can answer it as 3. Okay, is this clear or not? Clear. Next, preparation of alkyl halides from alkenes. Okay, alkyl halides are prepared from alkenes in two ways. One is monohaloalkanes, dihaloalkanes. Very, very important, especially this one. Addition of HX to okay, monohaloalkanes. See, it's a very preparation that is easy. From alkenes we are doing now. So anyways, this reaction will be studying multiple times. Just look at here. I will be explaining here only. You already have some idea on this. See, this is what alkene. Okay, to this alkene I am adding HX. What I am adding? HX. So HX is symmetrical or unsymmetrical reagent? See, symmetrical reagent means both groups should be of same nature. But here X, let us say halogen, like chlorine, bromine, iodine, like that you consider. Okay, so how it will break? This bond will be breaks as H plus X minus, right now. So unsymmetrical cleavage of bond is taking place. Now what happens? So this H place is taken by the double bonded carbons. So where it will be added, tell me? See, yes, see, here if we add hydrogen to this carbon, see, this is CH2, this is methyl and hydrogen here, right now. So if I add hydrogen here, we are going to get a positive charge on this carbon, right now. So now tell me what is the species generated here after adding H plus? This is CH3, CH, CH2. So I am adding hydrogen on the terminal carbon. So here I am adding. So positive charge will be generated here. Why? Because H plus is taken by the pi electrons of this alkene, right now. So now here you have a positive charge. So what type of carbon it is? Secondary. Now one more possibility, you tell me. I can add H plus here. I can add H plus here and positive charge generated will be on terminal carbon. So it means CH3, CH, CH2. Here I am adding H plus now. So yeah. So here plus. So now tell me, out of these two possibilities, which carbocation is more stable?
First.
See, to the given alkene, I can add H plus either on this carbon or on this carbon. If I add on this carbon, we will get a secondary carbocation. If I add H plus on this carbon, then you will get a positive charge on this carbon, because yes. So out of these two, which is more stable carbocation? Yes. So it means addition of H plus takes place in such a way to generate more stable carbocation. So which is more stable carbocation out of these two? So this one. So this will be taking majorly. So it will be minor amount. Okay. So now what is our major intermediate formed here? Secondary product, secondary carbocation. Now this will decide your major product and minor products. See, now from this, what will be the major product? See, here next what we have? Halide ion. No? So that halide ion can be added over here. So negative charge na, CH3, CH, CH3, here you can add X. Okay. Now here also you tell me?
CH3,
X minus, CH3, CH2, CH2, X. So it means which of these are major, minor, they will ask. So this is major and this is small quantity minor product. Okay. Do you got what we are solving here? Okay. Now see, in the exam question will be like this. Question will be like this. See, I am writing here, just follow me. CH3, CH, double bond, CH2. Addition of HBr they will say. Now tell me what will be your product formed here fast.
CH3.
What is the product formed here? Tell me fast.
CHBr, CH3.
Huh?
CH3, CHBr, CH3.
CH3,
CH,
BR.
CH3.
Why? See, we are adding first out of this HBr we will get H plus and Br minus. I already discussed in the last class also. Now tell me what about this HF, HCl, HBr, HI, which is more acidic here? stronger acidic, which is down the group acidic nature increases. See, we know, we studied about HCl most, like it's a strong acid, but HBr and HI is even stronger than your HCl. So down the group acidic nature increases, so HI is stronger acidic than HBr, HBr is stronger acidic than HF, HCl and HF, like that. Okay, is this clear? So based on this, HBr releases H plus ion, so that one, that H plus ion proton is abstracted by pi electrons. Okay, and on which carbon we should add? You should add in such a way to generate more stable carbocation. So it will be taken by this terminal carbon, okay, and you are getting CH3, CH, CH2. So on this you are adding hydrogen, right? So pi electrons are shifting towards it. See, not to make a bond between these two, a bond required 2 electrons. The 2 electrons coming from here, it means this carbon is losing the electrons. So it means here I should mention a positive charge, right? So this carbocation now, what is the anion here? Bromide ion. So it gives CH3, CH, CH3, here Br. Okay, this is your major product. Is this clear or not? Okay, now minor if means CH3, CH2, CH2, Br. That's it. I will explain that. Okay, is this clear up to here? Now you can make a statement now. What is the statement? See, whether it is HBr, HX I am writing. I am generalizing it as HX. Okay, so in this HBr or HX, what is the positive part and negative part? H plus is positive, Br minus is negative. So this is a molecule we are adding to the substrate, right? This is a molecule we are adding to the substrate. So you can say this is adding molecule or simply addendum. What I am saying? Addendum. So the negative part of addendum, what I am saying, see, negative part of addendum, where it is going, check here, the negative part of addendum going to the carbon is added to that carbon which contains least number of hydrogens of the alkene. So tell me here, the negative part, what is the negative part of this addendum? Br minus is added to the carbon which is having least number of hydrogens. So that is called Markovnikov rule addition. What is that rule called? Markovnikov rule. So see, we are not by hearting the concept. What we did? So we got that stability of carbocation. Based on stability of carbocation, we got our intermediate right now after adding H plus. So from that only we are making a major product and minor product. So now how do we got this major product from the observation? Based on stability of carbocation. Now there is a scientist who generalized a statement. So what is that statement? Markovnikov rule statement. What he says, the negative part of adding molecule goes to least number of hydrogen containing carbon is called Markovnikov rule. Okay, so why this point is very useful? Yes, there are many reactions without knowing the mechanism also. I mean, without writing all these mechanisms, you can directly remember the statement and you can make your product formation. Okay, so now once again one more example I am giving you here. Just tell me. To this you need to add HBr. Fast. Tell me. Where it will goes? Yes. So here you have this carbon contain 4 bonds. There is no hydrogen here. Here you have 1, 2, 3, 4. 1 hydrogen is there. So where do we have least number of hydrogens or no hydrogens? Out of these double bonded carbons, this is no hydrogens now. So negative part of addendum goes to here and hydrogen comes here. This is purely on mechanism only. Now statement is purely based on mechanism only. Okay, this is nothing magic here. Okay, so here bromine, here hydrogen. Okay, and remember addition of H and Br to the double bond follows trans addition. What addition? Trans addition. It means whatever the groups, what H and Br you are adding now, so one should be added from above the plane, other H and Br. H and Br should be in opposite plane to each other like this. If H is below the plane, Br should be above the plane like that. Okay, trans addition you can remember. Okay, next. Here, up to here it is clear. Now, I will explain you one more mechanism. See, you got the concept, right? So, now I am adding HBr only, but this HBr, tell me, where it will react? First of all,
Least hydrogen.
Where do we have least hydrogen? Here you have one hydrogen, here you have two hydrogens. Okay, first H plus, where H plus goes?
Most hydrogen.
There. Okay, here most hydrogen containing carbon. So you can add H plus to that carbon having more number of hydrogens of these alkene carbons. Okay. Here CH2 already we have two hydrogens, one new hydrogen is coming here, that's it. Okay, on this carbon you are generating a positive charge. Now look at this carbon, is it primary, secondary, tertiary? Secondary. Now if I shift one hydrogen from here to here, what happens to this carbocation? Get rearranges to tertiary. So tell me which is more stable, primary, secondary, tertiary carbocation, which is more stable? Tertiary. So that's why the rearrangement, proton like hydrate shift is taking place from here to here. So I can say carbocation rearrangement. This is not tautomerism. Tautomerism is different here. Okay, this is carbocation rearrangement. So why this carbocation rearrangement is taking place? Because a tertiary carbocation converts into tertiary, a secondary carbocation converts into tertiary, a less stable carbocation converting into more stable. That's why this process is taking place. Okay, finally this will be giving you. So what is the negative part of the molecule? Br minus, now. So that will be added over this positively charged carbon. So you will get a Br here. That's it. Okay, is this clear? Write this. Harshit, hi dear. One minute. Yes, Harshit, yes, whatever I am doing, yes, these are very useful for your preparation. Okay, and one more thing I will be explaining now. Just tell me based on your understanding. Tell me here fast. What will be the product formed? What will be the product formed during this process?
Secondary.
See here HBr, this is unsymmetrical alkene here, right? So where do we need to add H plus? So if you add H plus here on the terminal carbon, you will get a secondary carbocation here. But this is less stable. Therefore what happens? Proton shift like hydrate shift from here to here takes place, means carbocation rearrangement is taking place, right? Okay, so write the product here once formed. So proton shift, this will be taken first. So CH2 and one hydrogen is added, positive charge is here. This is secondary. Next what happens, tell me? Hydrate shift from here to there. Why it is shifting? Because it's a secondary carbocation. Even after shifting, this is also secondary carbocation, but that carbocation is in conjugation with the benzene ring. Right now that is what we can say benzyl carbocation is formed. We know benzyl carbocations are more stabilized by resonance effect. Okay, so that's why this carbocation rearrangement is taking place. Okay, because of its more stable carbocation is formed here. Okay, so next So now what is the negative part here? We have bromide ion. So add that bromide ion, that's it. Br, that's it. This is your final product. Okay? Clear? So those who are in online live session, is this clear or not? Whatever the mechanism I have mentioned here. Right, if this is clear, I will be giving you one more question. Please tell me based on your understanding. See what I am writing here. HBr. So what will be the product formed here? Tell me. What is the IUPAC name of product formed during this process? Very easy. Whoever in the live session can answer me this. Got the answer? So this is a 4-membered ring now. So what happens first of all? See, this is a 4-membered ring. We are adding HBr. First of all, add H plus ion. Where this H plus ion is added?
Center.
Double bond. Okay. So if I add here,
H plus at this side and positive charge in the middle.
so here positive charge, here H plus. So CH2H, and here it should be positive charge. Next, what happens? Tell me. We have bromide ion. Can I add directly bromide ion here or something happens here? No. What happens? This is a 4-membered ring now. So if I expand this 4-membered ring, what happens? It converts into 5-membered. So ring expansion is taking place. Why this ring expansion is taking place? See, if you observe, what is the angle in this square box? Cyclobutane means 90 degrees. 90 degrees is highly strained now, because sp3 carbon should have 109.5 degrees. Okay, but it is 90 degrees. So due to this bond angle strain, this 4-membered ring is highly strained, so always tries to expand it. Okay, so that we get a 5-membered ring here. So 5-membered ring is now little better than this 4-membered, because in 5-membered ring your angle 107 degrees around. Okay, so due to this reason, what happens? Ring expansion is taking place. So when it is expanding, just check where do we get the positive charge? Just check here. What are the things here we have? See, 1, 2, 3, 4, 5 I am writing. So you got a 5-membered ring as it is. Whatever the numbers we have given, write that 5-membered ring. Yes, and 5-membered ring we have. So between, see, if I say 1, 2, 3, 4, 5. So between which carbons it is forming a 5-membered ring? Between 5 and 1. So and 5 and 1. So which carbon should get a positive charge now? Tell me.
1.
See, this bond is disconnected by carbon, second carbon now. So second carbon should get a positive charge. That's it. Okay. And on first carbon we have an extra chain here, methyl. Okay. So to this what we need to add now? Bromide. So it will be giving us, that's it. This is the product form. Okay. Like this you need to do. Okay. Is this clear? Right. Let me explain few more things. So in all this discussion, what we have prepared? Mono-halo compounds are prepared using HBr. That is what? Addition of HBr to alkenes we discussed. Addition of HX. Okay, that's it. Next one is dihaloalkanes. What is this dihaloalkanes? See, same alkenes you take. Okay, to this what we are adding now? Cl2, like Cl2, CCl2, like this we are CCl, like in presence of CCl4, like non-polar solvent, like I am adding X2. Let us generalize this as X2. So what to do is, wherever we have double bonded, no? So on that carbon you add one X here, other X here. So addition of halogenation of alkenes also follows trans addition. Which addition? Trans addition. It means both halogens should be opposite in plane to each other. Okay, that's it. Okay, this is dihalo compound, we got it, no? So now just see here, I am writing CH3, CH double bond CH, CH3. So this I am asking you to add Br2. Now tell me what happens? Br2.
CHBr.
Br2 in CCl4. Tell me fast.
CH3.
CH3.
CHBr.
CH3. Okay, one bromine on the double bond carbon on other side and here one more. Like this. That's it now. So but it should be like trans to each other. Okay. Now one more thing you need to remember is bromine Br2 have reddish brown color. What is the color? Reddish brown. So whenever bromine is, see, just imagine initially in this alkene, in this container I have only alkene. What I have? Alkene. So to this alkene I am adding bromine water. What we are adding? Like Br2 I am adding. Okay. So bromine Br2, what is the color of Br2?
Brown.
Reddish brown. So now what happens? Whatever the Br2 is added, that will be reacting with the alkene. So it means whatever the Br2 we are adding completely consumed by alkene. So what happens to the reddish brown color? Will it be stays or it will be disappears? So it means the whether the compound given is saturated or unsaturated can be identified using bromine. Why? Because if it is an unsaturated compound, it can be alkyne or it can be alkene. Will be converting into a addition product like this. So it means whatever the bromine color is there, that will get disappears. Okay. So if I do same thing for alkene, does it happens or not? No. So it means for a saturated compound there is no disappearance of bromine reddish brown color. But if it is an unsaturated compound, yes, disappearance is taking place. It means we can able to distinguish or we can able to identify
which is
saturated or unsaturated. Okay, that's it. That is the application you need to remember here. The next. Here, see what I told you, addition of bromine is cis or trans? So, like halogenation is a trans, I told you. See, trans compound on trans addition. What do we mean by trans compound, trans alkene? It means in an alkene, if the same groups are opposite 180 degrees to each other, you can say it as trans. So this is a trans alkene. To this, what I am adding? Bromine. So it is also trans addition. See, bromine, one is above the plane, other one is below the plane. So like this now, okay. So this compound is called meso compound. What I am saying? Meso. Trans compound and trans addition, that is anti-addition, gives meso compound. So for like proper understanding can be given from this Fischer projection. What do we mean by Fischer projection here? Like this. So I am adding here CH3, here also CH3. Okay, from here to here, and one bromine here and other one is here bromine and other side hydrogen. See, so what do we mean by meso product here? It means if you pass a plane like this, what happens? See, this is a molecule. This compound can be written like this. Okay, so if I pass a plane like this, is it giving two equal halves or not?
Yes.
It is divided into two equal pieces now. So you can say plane of symmetry is present. What is that? Plane of symmetry. Whenever there is a plane of symmetry in the compound like this, so optically inactive. So meso compounds are optically inactive. Okay, now they will give in the exam. The product formed will be optically active or inactive. Okay, so now I will be making some statements. Please remember this. Whatever I am writing, symmetrical cis compound, symmetrical cis compound on cis addition. Symmetrical cis compound on cis addition gives meso. Next, symmetrical trans compound on trans addition gives meso. So both of them, symmetrical cis compound and cis addition, symmetrical trans compound and trans addition gives meso. So tell me, this is symmetrical trans or symmetrical cis or what? See, what do we mean by symmetrical? See, to the double bonded alkenes, like this alkene carbons are there now, both sides, whatever the groups here we have, it should be like same, like AA, like that. See, this side hydrogen, yes, here also hydrogen, here methyl. So symmetrical trans compound and trans addition giving us meso. Okay, like this you need to remember. Okay, next one is one more thing here, what I am writing, see, symmetrical cis compound on trans addition gives racemic mixture. What it will gives? Symmetrical trans compound on cis addition gives racemic mixture. These are the statements you must remember whether you are preparing for NEET, JEE or whatever the exam. Okay, we can expect questions from here directly. Okay, is this clear whatever I am explaining? See, to the trans compound we added in the trans fashion so that we are getting a meso product. Similarly, to the cis compound if I add in the cis fashion, it will be giving us meso. For a cis compound if I add in the trans manner, it will give racemic mixture. See, if opposite addition, racemic mixture, same addition, meso, that's it. Okay, that is about alkenes, addition of halogens to the alkenes we discussed. Then next here you can see alkyne is there, to alkynes we are adding halogens. Okay, so if we add, see what I am saying here, only 1 mole of X I am adding, X2 I am adding. So what to do? One halogen here, other halogen here. Okay, so it means R, C, double bond C, H. Here one halogen, here one halogen. This is 1 mole. This is partial addition I can say. One more pi bond. See how many pi bonds are there here. So one pi bond is removed by adding this H2. One more pi bond also we can remove adding one more H2. So it gives R, C, C, H, X, X as it is. Now I am adding one halogen here, one more over here. That's it. Okay. So what type of addition it see? See how many halogens are there? 1, 2, 3, 4. So tetrahaloalkenes are formed. Alkynes upon addition of halogens gives tetrahalo product. Okay, tetrahalo product is produced. Okay. So halogenation of alkynes gives a tetrahalo product, you can remember. Next, addition of hydrogen halide here. See, hydrogen halide. What we are doing? Addition of hydrogen halide. Okay, or hydrohalogenation. What we can say? Hydrohalogenation. So what is happening if you observe properly? On the same carbon, both halide ions are going. So you can say that is 1, 1 means it is a geminal. Okay, 1, 1 means geminal. So once again see here, to the alkene or C triple bond CH, you are adding HX. Okay, so again here also follow Markovnikov rule. See, this side is carbon, this side is hydrogen. Which carbon is having least number of hydrogen? See, R type, this one is having least number of hydrogen. So it should be, on this carbon it should be X, on the other carbon it should be H. Like least number of hydrogen containing carbon will take halogen. That is what Markovnikov rule, right? So R, C, double bond C, H you have, and you are newly adding one hydrogen here and one halogen over here. The next what happens, tell me, one more mole you can add. Okay, so it is also again same addition. So new hydrogen came, already one halogen is there, one more halogen. So and the same carbon we are adding two halogens. You can say geminal dihalides are formed. Geminal dihalides are formed upon addition of hydrogen halide to the alkyne. Okay, that's it. This is what you need to remember once again. Okay, right. Let us discuss few more things. Okay, so now if you see whatever the reactions we have studied till now, mostly you will be seeing preparation of bromides, alkyl bromides and preparation of alkyl chlorides. These things we have seen mostly, but preparation of alkyl fluorides and halides are very less right now. So here we have some specific reactions to be used for conversion of alkyl bromides, alkyl chlorides to fluorides and iodides. Okay, so there are two reactions. One is a Fink-Liston reaction, another one is Schwarz reaction. In both reactions, what we are doing? So conversion of alkyl chlorides or alkyl bromides to respect to alkyl fluorides or alkyl iodides. Okay, so now remember, one halogen exchanged by other halogen. Now, so I can say this reactions as halogen exchange reactions. What I am saying? Halogen exchange. See, halogen exchange method is used to obtain alkyl halides, especially fluorides and fluorides and iodides. Okay, so how it happens? See here. So there is one name, Fink-Liston reaction. What is the reaction called? Fink-Liston. So Fink-Liston is used to prepare alkyl iodides. For what purpose? Alkyl iodides. See, fluorides not F. See, fluorides not Finkel. For fluorides it is Schwarz. Okay, so for fluorides you can remember Schwarz. Okay, and for iodides it is Fink-Liston. What is that? Fink-Liston. Okay, so now first of all learn about this Fink-Liston. See, the inversion of configuration takes place in bimolecular nucleophilic substitution reaction. It means preparation of alkyl iodides follows which mechanism? SN2 mechanism. Which mechanism it is following? SN2. So SN2 mechanism, generally like they will ask which are the following reaction is an example of SN2, or which are the following reactions follows SN2 mechanism. So here you can remember Fink-Liston reaction. Next, the next chapter we will be studying about Williams and ether synthesis, that is also follows SN2 mechanism. Okay, now what happens here? See, alkyl bromide I have, so I am treating this with something like NaI in acetone, sodium iodide, like that I am taking and treating this in acetone. So why I am specifically mentioning this acetone? Yes, you can take any solvent that is polar aprotic. Which solvent I am saying? Polar aprotic. So polar aprotic solvents favors SN2 mechanism. So SN2 mechanism is favored by what? Polar aprotic solvents. So that you will get alkyl bromide, Ri is produced. That's it. This is the final product formed in the reaction. Okay. See, polar aprotic means it should not contain. See, I will tell you about solvents again, but listen here. So polar means the bond, whatever the bond present between them should be polar bond. Okay, aprotic means they should not form hydrogen bond. Especially if I want to say, we know hydrogen bond. If you observe, I already told you about this solvents. Do you remember in the last class only we discussed? You want example?
Hydrogen bond donor, hydrogen bond acid.
See, this is NN dimethyl formamide. What is this called? See, this is formamide, amide. This is amide or not? CONH2 means amide, right now. So here on the nitrogen we have two methyl groups. So you can say NN dimethyl formamide. Sir, why only you are constructing the molecule like this? See, it should not form, it should not act as hydrogen bond donor sites. If it is having hydrogen bond donor site, then it can be protic. See here, these hydrogen bonds, like hydrogen atoms are there in NH2. One minute. If they are like this, now what happens, tell me? So these, for formation of hydrogen bond, now here nitrogen hydrogen bond get participated in that, like hydrogen of this nitrogen get participated. So for formation of hydrogen bonding, this molecule is providing hydrogen atom. So you can say hydrogen bond donor. What is this? So if there is hydrogen bond donor site, you should say it as a polar protic solvent. This becomes polar protic. But what I am saying here, polar aprotic. So if I replace these two hydrogens, there is no hydrogen bond donor site in the molecule. So that makes it to be polar aprotic. Okay, do you got the difference between polar protic and aprotic? See, polar bonds are there everywhere. See, between carbon and oxygen, see, due to electronegativity difference, this bond get polarized. polar bonds are there, but aprotic site is important. Aprotic means there should not be any hydrogen bond donor site. So in the first molecule there is no donor site. So you can say NN. So in the short form it is called as DMF. What I am saying? DMF means dimethyl formamide. What is that? Dimethyl formamide. Okay. Next, one more solvent, one more example if you want, you can write DMSO. Can you expand this? Dimethyl sulfoxide. What is that? See, sulfur, oxide means oxide bond should be there. Then next dimethyl, this side one methyl group and one more methyl group over here. That's it. Okay, do you got the difference? Whether tell me it is polar protic or aprotic? Aprotic, because polar bond is there but not any hydrogen bond donor sites to form hydrogen bonding right now. So polar aprotic. Is this clear? Right. Am I raising? Okay, so clear now? Finkelstein reaction. Next. So Schwarz reaction, see, conversion of alkyl bromides, alkyl chlorides using this specific reagent. See, what are the reagents we are using? In all this, fluoride ion is coming out. AgF, SbF3, COF2, Hg2F2. What they will do? They will replace bromides or chlorides from alkyl halides from substrate and converts into fluorides. So what is this? Schwarz reaction. So Finkelstein means for preparation of iodides follows SN2 and this is Schwarz reaction. Okay. Next, one more thing, it is also very important, just listen here. Preparation of allylic halides. What do we mean by allylic halides? Again, allylic halides is very important topic. This is, just give me a minute for having some water. Ever book? Look at here. What to do? See here, preparation of allylic halides. What do we mean by allylic halides? First, in the first day, classification of haloalkanes itself we discussed. Allylic means it should be like this: CH2 double bond CH, CH2 Cl, like this. It means halogen atom should be present on sp3 hybridized carbon. That sp3 hybridized carbon attached to the sp2 carbons. Okay, so there should be double bond system, alkene system attached to sp3 carbon on which chlorine is present. Okay, this is what allylic chloride I can say. Okay, so now it can be in any manner. See, I am writing a 5-membered ring here and a double bond I am placing here. Now tell me, what are the allylic sites to this double bond? The adjacent carbon, yes, this one or this one. Okay, here if you place this chlorine, yes, this is a allylic chloride right now. That's it. So this is how you need to identify allylic halides first. Okay, so how it is important, let us see, and how can we prepare them? Very easy. Just see here. See, there is something called a brominating agent. In name of that compound is NBS, N-bromosuccinamide. What is that? N-bromosuccinamide. So this is the structure. See, on nitrogen we have bromine now. So that's why N-bromo. Okay, N-bromosuccinamide. So here I have mentioned brominating agent. N-bromosuccinamide is used for preparation of allylic bromides. For what purpose we are using them? Preparation of allylic bromide. Okay, so look at here. So how can we prepare this? Are very easy. Just look at here. What I am writing? CH3 site is there. So NBS. I am writing like this. So where this reaction takes place? See, whenever you are seeing bromine like NBS, so you just remember N-bromo, no? So it will give us bromine. What it will give? Bromine radical. Okay, so where it happens? See, do not disturb this double bonded carbon. Adjacent carbon is there now. So there you replace hydrogen by this bromine, so that you will get
Allylic.
bromine. So it is allylic position only now, right? So you can say allylic bromination is taking place. Okay, is this clear? Right. So not only allylic, one more compound is there called benzylic. What I am saying? So benzylic means similar to this, benzene ring will be there here. So this is a benzene ring. Okay, on this benzene ring the next carbon will be there now. This carbon. So this carbon is called benzylic carbon. Okay, see on okay. So what I am saying? So this position is called benzylic position, right? So you can write it as CH3. Okay. So on this position, one of the hydrogen is now replaced by bromine whenever you are using NBS. So what is the product formed here?
Benzylic bromine.
CH2Br. That's it. Okay. Most generally it will happens in non-polar solvents like CCl4. Okay. So benzylic bromination, allylic bromination is taking place with the help of NBS. Okay, this is what you need to remember. Okay, this is what you need to remember here. So just tell me here what happens. I am writing one more. NBS CCl4. What will be the product form? Tell me fast. Where the reaction takes place?
Allylic site.
Yes, where do we have allylic site?
This side and that side.
Here you have allylic site with respect to this double bond, adjacent carbons are allylic. Okay, so yes, this is also allylic. But what we are observing here, see, there are three hydrogens. One hydrogen is replaced by bromine, so that it is becoming CH2Br. So what will be the primary criteria here? You need to see here. Whenever you are looking at the allylic sites, there should be minimum of one hydrogen to replace by bromine. Do we have hydrogens here? No. All two hydrogens are substituted by methyl groups only, na, this side. So no reaction at this allylic carbon, only taking place at here, because there we have hydrogen. So there should be a minimum of one hydrogen for substitution, like at allylic position. So you will get bromine here, but there is no reaction here, remains as it is, like this. Is this clear, whatever I am explaining? Right. So in the same manner, now I will be giving you one more. So tell me fast, what happens and where it happens?
Benzylic bromide.
Huh?
Benzylic.
Above or below? Both. Here there, see, this is a carbon, benzylic carbon, but there is no hydrogens now. So you can say no hydrogens to replace. So no reaction site, not a reaction site. So it is not a reaction site. So what is the primary criteria? At least
One hydrogen to be replaced.
at least one allylic hydrogen atom should present to substituted by bromine of NBS. Right now, this is what you make a one single line on your own words, so that whenever you are reading now, you will feel like you got everything. So now tell me where it happens, only above side. So the product formed will be CH3, CH2, Br, and here no reaction, like this as it is. Okay, is this clear? That's it. Okay, sir, I wanted to do chlorination. So what you can do? See, sometimes instead of mentioning as NBS, in very few cases it is mentioned as N-chlorosuccinamide, NCS I am saying. It's very few cases. Okay, so few books contains like N-chlorosuccinamide also. Now what happens? In the place of bromine we will get a chlorine. Okay, CH2Cl like this. Okay, and the next one is, yes, cartoon kids above, it is really good. And the next one is, here instead of doing this I can also take alkene and can treat this with chlorine in presence of sunlight. What happens, tell me where it happens?
CH terminal.
Yes, so in presence of sunlight, whatever the mechanisms we have seen, all the reactions you have seen, this follows free radical substitution only. Okay, now what happens? Here you will get, wherever this allylic position is there, there will get a chlorine like this, CH2Cl. Okay, so same reaction may also be mentioned with chlorine under heating condition or some high temperature like 500 to 600 degrees Celsius also they mention. So products will be formed same like this. Okay, remember. Yeah, so the next one here, yeah, next reactions here will be discussed. Clear up to here? So tell me, the given compound is an example of, see, this is a NEET, very simple question.
Allylic halide.
How it is? Double bonded carbons, adjacent carbon is there on which halogen is present. So which one it is? Allylic halide. Tell me this one, which of the following is an example of alkyl aryl halide? Alkyl aryl halide.
Allyl chloride.
So write the structures. Write the structures. Parachlorotoluene. What do we mean by toluene?
CH3
Cl. Parachlorotoluene. This one chlorobenzene.
Cl.
Benzene with chlorine. Phenyl ring with chlorine. So this is nothing but aryl chloride.
First one P.
Okay. Now here you can see allyl chloride. It means it should be simply like this. Benzyl chloride. It means CH2Cl. Okay. Which are the following is an example of alkyl aryl chloride. Alkyl group should be there, aryl group should be there. Yes. Which one? First one. Okay, that's it. Then next. See, preparation of haloalkanes from carbonyl compounds. Carbonyl compounds means first you need to take C double bond O R like this now. This is carbonyl compound. Just treat this with PCl5. What happens, tell me? PCl5. In PCl5 there are two weaker chlorine bonds right now. Axial bonds are weaker. So the two chlorine atoms comes out, that will replaces oxygen. So oxygen is given to phosphorus, two chlorines are taken by carbon. So you will get R, C, R and one chlorine above and below. I am writing like this. Dihalo compound is formed here. Okay, POCl3 is byproduct here. Okay, is this clear? Okay, about this carboxylic acid again I will explain, just hold on. Okay, this is clear or not, carbonyl groups? Next. So tell me this one. Which of the following is not an example? Which of the following is not an example of allylic halide? Write the structures. Not an example of allylic halide. So write the structure of this 1-chloro fast. What they are saying, sorry, what they are saying, but 1-ene, but 1-ene, 4-chloro, but 1-ene. So is this allylic? No. Here if we have halogen, it is allylic. So this is not an allylic. So not an example. So first one is not an example. Next one, 1-chloro, but 2-ene. See, but 2-ene means first you write, this is but 2-ene. 1-chloro means here or here you can put 1-chlorine. Yes. Yes. Allylic. Next, what about this one? 3-chloro. So how do you write the structure? 3-chloro. But 1-ene, 2-methyl, 3-chloro. Yes, tell me. This one also allylic, na? See, this is a sp2 carbon attached to an sp3 on which chlorine is present. Allylic. Next one, this one. 4-chloro pent-2-ene. Just identify on yourself. Pent. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Pent. Pent-2-ene. 4-chloro. Okay, like this. And first one is what? But 1-ene. 1-ene, 2, 3, 4. Yes. So here we are getting two options now. So what are the two? First and fourth. Yes, first and fourth. Both of them are not allylic one. Okay. Yes. Actually it should be one answer only, but anyways we are getting two. Once again we will verify with first and fourth. So but 1-ene, 1, 2, 3, 4. Yes. This is not an allylic. Okay. Next one, what about this? 1, 2, 3, 4, 5. Okay. So 2-ene. Yes, this is 2-ene. 1, 2, 3, 4, 5. Pent-2-ene. 2, 3. See. 4. Hey, this is allylic only now. So not 4, only 1. Okay, that's what. So you need to verify all the time. Be conscious. Do not care about others. Okay, right. So only first option is correct. Okay, right. Next. So what are the preparation methods we have followed till now? See, from alkanes we have followed free radical halogenation, and that is giving us alkyl halide. For example, here I will be giving you one exemplar question. Just tell me CH3, CH, double bond CH2. So to this I am asking you to add chlorine CCl4. Asking chlorine in presence of H nu. So tell me what happens. What are the products formed here?
Hydrogen goes to this side and 2-chloro. Dihalides are formed.
Tell me what are the products. Those who are in the live session can also answer me. What are the IUPAC names of these products formed? You can write in the chat box if you know the answers.
Germinal dihalide.
Yes. See,
dihalide.
whenever it is chlorination in presence of CCl4, where the reaction takes place, there is a lot of difference between both reactions. Wherever we have unsaturation pi bond, their reaction takes place. Remove double bond, place two chlorines. That's it. So it means CH3, CH, the double bond is removed, CH2, and you place on the carbons two chlorines like this. Trans addition it should be. right now. Chlorine, that's it. Now what about this one? Chlorination in presence of sunlight, where it happens? It should not be taking place at unsaturation carbons, it should be taking place at allylic position. Okay, it means what is the product form, tell me? CH2 double bond CH, CH2 Cl. This is what the product form. Okay, you need to know the difference between two reactions. Okay, that's it. Then next, from preparation of alkyl halides from alcohols also discussed very clearly. Okay, and even in today's reaction discussion also we did. Okay, carbonyl compounds like with PCl5 will get. Okay, from alkyl halides, Finkelstein reaction, Schwarz reaction, halogen exchange reactions we discussed, right? And the next one here, from alkanes, addition of X2, HX. This is from alkanes, not alkanes, this is from alkynes. Alkynes. Okay, even from alkanes already we discussed here, from alkanes, and this is from alkenes. Okay, these are the things we discussed. Okay, this is alkenes, this is from alkenes, this is from alkynes, right? That's it. Why I am saying this is from alkynes, this is a alpha halogenation. That alpha halogenation is nothing but allylic products we have seen now, that is what alpha halogenation. Remaining two things same here and there. Okay, that's it. Okay, the next, preparation of aryl halides and haloarenes. It means till now we have prepared what?
Alkyl halides.
Like haloalkanes we prepared, and now we will be discussing about aryl. What do we mean by aryl? It is a derivatives of benzene rings we can say. Okay, so halogenation of benzene, so that is nothing but you take benzene and to this what halogen, but it should be in presence of some Lewis acid. Like if it is chlorination, you can say Cl2 anhydrous form of AlCl3. So what it will give? Chlorobenzene will be produced here. And what is the electrophile involved here? See, first of all, chlorine and anhydrous AlCl3 reacts chlorine AlCl3. So this together what it will form? See, here you have vacant orbital, lone pairs given here. So chlorine is removed with the pi sigma bond. So not homolytic, it is heterolytic. Like this you will get AlCl4. So heterolytic cleavage taking place to give chlorine cation. Okay, chlorine cation is our electrophile here. Like you can say halonium ion or it is chlorine cation. So this is our electrophile. Okay, so now to this electrophile we need to give some electrons. Who will be giving here? Our substrate. What is our substrate here? Benzene. So benzene contains pi electron, right? Yes. So pi electrons can be given to this chlorine. So now what is happening here? Chlorine positive charge, like this you are seeing. Okay, this positive charge can be stabilized by conjugations like this, right now. So this what type of conjugation we can say? This is pi cation conjugation, right? So completely you can call it as sigma complex. What I am saying? Sigma complex, or carbocation formed or sigma complex you can say. So this sigma complex is stabilized by pi electron conjugation with the empty orbital of carbon.
Sir, FeCl3 can also be used, right?
Huh? Yes, FeCl3 can also be used, anhydrous form only. Okay, so now look at here, positive charge here, you can shift like this again. So these are resonating structure. I hope you are already familiar with this.
7 canonical forms.
Like this. Okay, now finally if you see, wherever the chlorine is added and that carbon we have already one hydrogen. Initially it is sp2 carbons, all of them, but after adding chlorine electrophile it is becoming a sp3. See, aromatic ring becoming a non-aromatic compound right now. So which is more stable? Aromatic. So it means aromatic should be regained again. So how it possible? First, these are the possible resonating structures we are writing, I mean sigma complex stabilization I am explaining. After this, finally you should get a product. How it happens? Wherever the chlorine attached carbon is there now, so from that carbon you remove proton. So deprotonation is taking place and it will be giving you finally as a 1, like here double bond, one more double bond, one more. So if you want I will write it clearly here, just see like this. Sir, no? So here you have one chlorine. So this is nothing but our chlorobenzene. So now what are the steps you have seen? First step is generation of electrophile. Second step is attack of electrophile on the benzene ring, that is what? Formation of sigma complex. Final step is deprotonation. So these are the 3 steps involved. Now what are the things you have seen from here to here? One hydrogen atom is replaced by chlorine. So it means a substitution only now. One player is substituted by another player. Substitution. Okay. And what type of substitution? Electrophile is substituted. And in which one it is? In a aromatic ring. So you can simply call it as aromatic electrophilic substitution reaction. What is this? Aromatic electrophilic substitution reaction. Now how many steps are there in aromatic electrophilic substitution?
3 steps.
3 steps. First step is called generation of carbocation. Second step, formation of sigma complex or attacking of electrophile. Okay. Then third step is deprotonation to regain its aromatic nature of that ring. Okay. These are the 3 steps. Okay. This is done now up to halogenation. What mechanism I told you here? Aromatic electrophilic substitution reaction mechanism. Okay. So about Sandemeyer reactions and the next Gutterman reaction we will be discussing in the next class. Okay. So just stay connected with our NEET World channel. I hope whatever we discussed till now are completely clear. Okay. If you want any PYQs related to this, just consider these and try to solve them. If you have any confusions, you can watch tomorrow's session on the same discussion. See, today only we discussed about like alkyl bromide with NaI. What is that reaction?
Finkelstein.
Yes, Finkelstein. Okay, this is Finkelstein. Now what they are asking, identify Schwarz reaction. Tell me, what is our Schwarz reaction?
D.
Fluorination. Right now, halogen bromide exchanged by fluorine. Okay, like that. You can solve few more questions here. SN1, SN, tomorrow we will do about this. Yes. So from today's discussion only.
RI.
Swinkel 1, B1, B1,
C2.
C2, B1, C2, B1, C2, B1, C2, fourth option, that's it. Right. So the remaining things that are required we will be studying in next class. Okay, right. So you can solve some questions from any of your PYQ books, or otherwise go to our website and you can check, some questions will be uploaded. You can do that. Okay, thanks for watching. Stay connected. Thank you.